Today, I'm going to be talking a little bit more. We'll do some exercises on secretion and absorption, how to use those features. And then we'll talk about building a little toy tumor, avascular tumor growth model using uptake and secretion to do that. And then if we have time, I'd like to talk about how to do chemotaxis. And when we've done those things, there still are quite a few features in CompuCell, like compartmental cells and links, that we haven't covered, but we'll have covered all. Once you've done those things that we've covered today and maybe next week, uh, that will really cover almost all of the core things you need to be able to do in CompuCell. And some of the things that additional features we can cover, but the basic sort of introductory CompuCell will be covered by that, and there's a lot more, but that's the basics. So I wanted to. Right. Hold on a second. Having said all that, now I wait a second. I opened the wrong. I apologize. Boy, am I out of it. I opened the wrong slide deck. What I said earlier was still true, but I had the wrong slide deck. The reason I didn't recognize it instantly was that a lot of the slides, that was last year's deck that I was showing you, and a lot of the slides actually were the same in both decks. But I changed the material a little bit to correspond to what we've done in class so far. So I want to remind you of these basic concepts of diffusion length, diffusion time, and equilibration time, which are important modeling concepts that aren't tied to CompuCell. I'll remind you how secretion is done and uptake are done, because we covered those, but very quickly last week. And then we'll do a couple of very simple exercises on that to make sure that it behaves the way you think it should. And then after that, we'll try building in steps a very simple avascular tumor model. So we'll take our basic cell growth model and add a little switch of quiescent necrotic proliferating type due to uptake. It's not going to be very realistic, but it'll give us an example of how you would do those things to build a more realistic model. And if you wanted to build, say, an uptake model for bacteria, you'd use the same syntax. So I think that's useful. And then again, I have here something referencing Fetocell Pi, but if Pedro's not here, we're not going to do that. I'm not a Fetocell Pi user. He knows how to use it. And then again, if we have time, we'll talk a little bit about chemotaxis. And as I said earlier, that completes all of the basic modules for CompuCell. There are plenty of more sophisticated modules that you could use, but that gives us the basics. So one of the things that we talked about last week was how to control the field window in Player, and in particular for chemical fields, sometimes you'll want to use fixed ranges of the chemical fields. Sometimes you'll want to use float. Often you'll make the bottom of the value 0 and then the top a float auto scale. And then also you have this scalar contours, which can be quite useful to help you understand what the shape of complex fields is. It's hard by eye. If you have color gradients, it's actually hard to estimate the gradients by eye. So that's useful. The other thing that is quite useful, which we didn't actually do in class, although it was in the slide deck, is this very simple code. You say field is self.get concentration field. You actually don't even need get concentration field. You could just say self.field and then the name of the field name. This is old syntax. This will still work. And then we go across the, say, the x-axis of our field, read the values, and then plot them. Because a lot of times you really would like to be able to have a graph that shows the concentration in a particular region, as well as the color plot. And so I'm going to ask you to do that coding. Again, you don't need to use this get concentration field syntax. If you go into the TWIDIT and go under chemical field manipulation, it has the new one, which will be just field equals self.field.file. This is, again, this will still work, but it's older syntax. Everything else is the same. You read the field values and concentrate at a position just with a square brackets, and then you can plot the values like that. One thing I will say is that plotting and replotting fields in this way is fairly slow. So you might not want to plot them every Monte Carlo step. For classwork where you're looking at how things are going, and these aren't big simulations, it's not a big deal. But if you're going to do production code, you wouldn't want to be doing this every Monte Carlo step. There's a function here which we haven't talked about, although it's in the scientific plots function, which is self PW is here for short for plot window, erase all data, and that will blank the screen, because sometimes you want to see how the curves evolve over time, but sometimes if there are too many curves overlaid on each other, it's difficult to see what's going on. So again, the online manuals for CompuCell talk about the syntax for that, and the TWIDIT code snippets provide that. But if you don't know it's there, then you don't know to look for it. All right. So I want to come back to here, starting with the diffusion equation. Here we have diffusion with a constant, diffusion constant, and then a decay constant, first order decay constant. And it's worth remembering that typical diffusion constants for a small ion like potassium or sodium are 2,000 microns squared per second. For a small protein, about 5 to 10 microns squared per second. And for a large molecule like DNA, on the order of 10 to the minus fourth microns squared per second. And here GFP is a little bigger. A smaller protein might be 100 microns squared per second. And so that gives you a sense of what the typical time things take to diffuse is of a given distance. If one really doesn't know anything about a molecule and you want to get a rough estimate of the diffusion constant, I'm not teaching a physics course, but if you look up the Stokes-Einstein relation, you could type in the molecular weight. They're online calculators, or for that matter, Google will do it for you now because it knows that. You say, what is the diffusion constant, assuming Stokes-Einstein and you give molecular weight, and it'll give you an estimated diffusion coefficient. The actual diffusion coefficients are almost always a little less than the Stokes-Einstein estimate, but they're within an order of magnitude. So that's a helpful thing. If you don't have any information, that's the place to start, because otherwise you say, I have some protein, I have no idea what the diffusion coefficient is. Stokes-Einstein will help you with that. The reason I'm not presenting it in detail here is I don't want to have to do the derivation, which is sort of long, but it's worth looking it up. If we were in a physics course, it's actually quite an interesting derivation. And it's one of the things Einstein actually won the Nobel Prize for back in 1916, whatever. But so the things that we really care about are not the diffusion constant, decay constant per se, but rather the diffusion time, how long it takes a molecule to diffuse a distant cell, which goes like the square of the distance divided by d. So diffusion gets slow over long distances. The diffusion length, when there's decay, how far a molecule typically gets before it decays or is absorbed. That's like the square root of d over gamma. And then the time to equilibrate, which is just 1 over gamma. And so all of these are useful numbers. In reality, the reason there are approximations here is that the actual numbers may have a factor of 2 or 4 or pi in front of them. But what really matters is the scaling. It goes like L squared over D, it looks like D over gamma, it looks like 1 over D. And these are really the critical things, especially diffusion length is very important in biology. Diffusion time also can be important. All right. So when we're going to use secretion or absorption in Multicell, and this will seem similar, I think, to Paul and his rule grammar, you have to say which cells or generalized cell objects secrete or absorb, where that secretion and absorption happens, because with spatially extended cells, you have to say, does it happen at the surface of the cell, inside or outside the surface, over the whole area of the cell, at the center of the cell? There are these multiple options. And then also, does it happen everywhere or just where the cell is in contact with other cells of a given type? And then for secretion, not for absorption, do you have constant flux or do you have constant value boundary conditions? And again, there's this slight strangeness, which is not the case with most CompuCell plugins, which is that you can specify secretion and absorption in the diffusion solver, the secretion plugin, and in Python. And if you specify the secretion multiple times or absorption multiple times, it's repeated. It'll do it multiple times. The syntax is sort of similar. It was supposed to be identical. It's not quite identical. Within the diffusion steppable, there's a block called secretion data. You specify this cell types that secrete. This is constant flux, constant rate. And there are secrete on contact options. There are constant concentration options for different cell types. For the secretion plugin, you have one secretion plugin for all the fields that you want. So the secretion plugin and then field name, the name from the PD solver. And then again, secretion type, then the cell name. So that matches from the other one. And then again, secretion on contact or on contact with, and then the type names. And you can also have constant concentration. So the syntax is the same. If you don't remember the syntax, the Twit will help you remember it. As usual, if you're going to do secretion in the steppables, you don't want to have anything in the secretion You have the following options: inside cell at boundary, inside cell at boundary on contact, inside cell at the center, everywhere inside the cell, outside the cell at the boundary, and outside the cell at the boundary on contact. So there are 1, 2, 3, 4, 5, 6 different locations you can select to secrete. And there also is this option, which is what's called with total count, which returns how much was absorbed or secreted during each step. And what's returned is actually not a number, but an object. And so to get the actual number, you have to go to here, amount secreted equals the result dot total underscore amount. And again, if you forget this, the manuals go into all the detail. There are examples in the demos, and there also is the Twit to help out, because there are a lot of different permutations. Something that could be a little bit confusing when you do at boundary on contact, it's not, it's a list of the type names. So cell, the cell, the secretion rate, and then a list of the type names that you're going to be on contact with, and not just the names themselves. There are also a couple of simple things that you might want. There is total field integral that gives you the total amount of chemical in the field, which is a useful number to normalize things. Amount seen by cell will get you the amount in all the pixels occupied by the cell. That's also quite useful. So there are these options that you have. To be honest, I forget all of the permutations. There are a lot of combinations. With uptake, we in general need to use the Python to do controlled uptake. There's some general uptake functions, but they're not that helpful in the XML. As I mentioned, we really would like to have a sigmoidal or a Michaelis shape, but we don't. What we have is linear uptake followed by a maximum. That's not so far from a Michaelis shape, really. And so you have two numbers. You have to specify the fractional uptake for small concentrations and the maximum uptake. And it's not auto-scaled, so you have to adjust that if the time scale or the amount in the chemical change, you have to change those numbers by hand. The other thing to remember is that uptake operates on a per pixel basis. And so this is uptake per pixel or per voxel. And so if your cell, suppose you do uptake over the entire cell, and the cell has a volume of 30, then you'll typically get a number that's 30 times bigger than this. So we often will wind up dividing this uptake amount by the volume of the cell to get the uptake per vox. And when we do uptake, almost always we want to know how much we took up, because we're doing something with it. And so that total count feature is quite important in those cases. And for reasons best known to the designers of CompuCell in the distant past, the amount taken up is always returned as a negative number. And so you'll have to put a minus sign in front of it. It's basically thinks from the perspective of the field, so it gives you a negative number. So don't be surprised about it. And by the way, I hope you found it. All of the slides decks are available to you the Google Drive I shared has all the slide decks, so you can always go back and look at the slides. So if you have trouble finding the slides for any lecture, let me know. And also, if you want to work ahead, the slides from previous years and also from the summer courses are always available as well. So that material is all there. In the summer courses, sometimes the teaching is a little bit different because, for example, maybe Pedro taught a lecture or Giuliano or Giulio taught a lecture. And so they cover the same material, but with maybe a slightly different point of view. Sometimes they'll use the same slides, but sometimes a different point of view. So if there's something that I say that's confusing, those summer course slides might be sometimes have a different perspective on the same question, and so they might be helpful. Again, if you want to look at that, if you have trouble finding that, let me know and I'll make sure you're pointed to. All right. So again, on uptake at a constant value doesn't make any sense, but you still have all the regions inside at boundary on contact, inside center of mass. That doesn't really make sense for uptake. Inside everywhere in the cell, outside the cell at the boundary, outside the cell at the boundary with contact. In that case, you want the plugin just to be the bare plugin. Plugin name equals secretion. That's it. And then to specify it in Python, what do you have to do? You have to be able to say what field you want to take the chemical out of, because there may be many fields. So you have to have a reference, you have to have a handle to the particular chemical field that you're going to take the chemical out of. And so that would be, here I called it attractor secretor equals self.getField secretor, and then the name of the field. And the same attractor secretor works for both secretion and uptake. You don't have to do it twice. And you also don't actually have to get this reference more than once. You can put it in the step function, but you could even do it in the start function and then pass the reference through a dictionary if you wanted to. But don't put this inside of a loop, because it's slow. Getting the reference takes time, and you certainly don't need to do it more than once per Monte Carlo step. And then once you've done it, you have here attractor secretor. That's the handle for the chemical field. And then you have the function or the method. This would be uptake outside cell at boundary total count. It's long because there are all these permutations. The cell ID, the maximum about to take up, and the fractional about to take up. And that will return, you notice you've got res equals that, amount equals minus res dot tot underscore amount. And that will return how much chemical you pulled in. Okay. And so one other thing to remember, in addition to that list of diffusion length, diffusion time, equilibration time, that's important, and this is for secretion, is if you have a secretion at a constant rate S and a decay rate of gamma or uptake rate of gamma, then at equilibrium, the concentration is S over gamma. And so if you change gamma, then you need to rescale S to keep the equilibrium concentration the same. And so it's useful always in the back of your mind to have this equilibrium concentration S over gamma, because sometimes if you're having things secrete or absorb, the chemical concentration will seem to run away, gets to be bigger than you expect or smaller than you expect. And so it's good to have an idea of what the values should be to get the scaling you want. So if, For example, you want to imagine that the chemical concentration should always be around 1, or maximum should be around 1, then the secretion rate divided by the decay rate has to be about 1. Typically, we pick the decay rate first because that sets the time scale of the system. And so if the decay rate is 0.0001, and you want the chemical concentration to be 1, then the maximum secretion rate is 0.0001. So conceptually, if you're going to do this, and I really should write a little article on this, although I think Stan Murray's article is pretty good about it. If you're going to think about designing a simulation to match an experiment, the first question you would ask is, what is the diffusion length? How far does the chemical get typically in the system? That's usually known pretty well in experiments. This VEGF-A or TGF-beta gets typically 100 microns. So it tells 10 cell diameters. And so then you say, okay, if the diffusion length is 100 microns, then your next step is to say, well, that means the square root of diffusion divided by decay has to be on the order of 100 microns. And then typically what will happen is you'll say the real diffusion constant for the chemical is quite large. We're using time steps of 1 minute per Monte Carlo step. And that would mean that the diffusion constant is thousands, for example. And that's very slow computationally. So then you would divide that by 1,000, but then you divide the decay constant by 1,000 as well to make things match, to keep the diffusion length the same. And then similarly, you'd have to make the secretion rate 1,000 times smaller too, so that the chemical concentration doesn't blow up. Does that make sense? When you do it, once you start playing with it, it'll make more sense. As an abstraction, it's words, but when you actually do it, you'll see right away that that's it. But that order of choice, which is diffusion length first, rough estimate of diffusion constant. If the diffusion constant is too big, adjust the decay constant so that the diffusion length is correct. Again, for chemicals like oxygen that diffuse very, very fast, if you tried to actually implement the actual oxygen diffusion, the simulations would be so slow you wouldn't get anything down. So let's just practice a little bit here. Create a single cell, say 100 by 100 lattice, so that it's not too big, so it doesn't take too long to run. Create a single frozen cell of the center of the simulation, single chemical field. Use the secretion plug-in. Set the diffusion coefficient to be 1, the decay constant to be 0.01. So that means what? The diffusion length is 1 divided by 100. So that's 100. Square root is 10. So that's the diffusion length is about 10 voxels. Set the boundary condition to be constant values of 10 at the boundaries. I'm not actually sure why I did that. I think I would think that we would want, for secretion, I would think we would want to set it 0 on the boundaries, but we can come back to that. And now, use that little code that I showed you to scan across the middle of the simulation and plot the concentration as a function of position in the x direction. And then I want you to run the simulation, and we'll switch for the secretion inside cell at boundary, secretion inside cell at center of mass, outside cell at boundary. And switching from these between one and the other one of these is changing one, not even a full line of code. It's just changing the secretor command. So once you have the code to create the field, draw the plot, it's pretty quick. So what do you think it's okay? Can you take a few minutes and write code?
Yeah, just try to create a new project and try if I can process
Okay.
these steps.
So
Okay.
why don't I give you five, you you take as long as you need. If you need help, that's okay
Okay.
too. Why don't you work on it on your own for a few minutes?
Hmm.
And then if you want to share a screen and ask questions or need advice, I'm happy to help out. Okay.
Yeah. Okay, great.
If you need any help or you want me to look at something, just say so and I can turn the screen share over to you and we can look at it.
Okay. I see like not a problem. And now I'm requesting for sharing screen.
Okay.
Oh, okay, I'm a co-host, so I think I should be able to share it. Um, okay, so I would like to um cache like have a reference of the field and then like fetch the value of a specific position.
So
And I kind of like forget. I tried the print C at first, but it says
no,
like
that
invalid
that
syntax.
that looks okay, but I can see one problem right away with that. Although it shouldn't matter too much because you only have one cell, is that right?
Mm-hmm.
So I don't think you want to put the plot of the scan of the chemical concentration inside of a four cell loop.
Oh,
You don't probably want to put
you
that
think
inside of a cell.
you think like you should put this like after you iterate
No, no,
every
but look at line 34.
okay, then this one.
Why? So if you run this now, what happens?
It will like do this kind of
But just
like
show me, why don't you show me what happens when you run it?
oh now it doesn't work actually because
What's the
um it will report error like invalid syntax. It will show here,
right?
so that means like
So what is
uh
the correct syntax for the field? Take a look at go up to the CC3D Python,
okay
just duplicate, and then chemotaxis, I'm
then
sorry, chemical field manipulation, get field value.
yep
Okay, that's right. So what you need is a get field reference. I'm sorry, get
yeah
refield
yeah
reference.
uh,
Okay, there we go. So it doesn't go in
yeah
parentheses and no quotation.
no quotation. Oh, okay.
It's just the name of the field.
Oh, okay.
Try that.
I thought, okay, I'll try. Maybe I should, maybe like I should use the non-capitalized version.
So again, in Python, capitalization matters. So whatever you called it in the XML, you have to be matched. So where's the XML? Where's your XML?
Um, Here, oh, it's not, it doesn't
Okay, so it
capitalize.
is lowercase. Okay, so that should be all right.
Okay, now I'm
So
trying
now
to
try
run it.
running it.
It crashed just now. Yeah.
Okay, but it started. So the problem
Okay.
is, where did it die on you? Uh,
Um, I think here it's should be like dimension, unmatched dimension.
okay. Oh, I see why. I think. Let's see. Let's look at the
Mhm.
field. It's okay. Hmm. Okay, well, so one thing it shouldn't cause the crash, but you do not want to get the field reference inside of a loop. So 35 should be outside of the loop.
Um,
36 needs to be inside the loop, but 35 should not be inside the loop.
oh, okay, okay, I see. So like, um, maybe I should take
Well,
this out of it.
everything should be outside of the four cell loop.
Oh,
Uh,
okay.
but okay.
Oh, let me try this
So
again.
all you have to do is not indent lines 35. So line 31, that's fine. So don't indent line 35. You don't want it inside the four cell loop.
Mm. You mean like cancel the indent here?
Yes, that's right. You can use the arrows above the green and red button arrows for indentation. Up if you look up in the
Oh,
toolbar,
mhm.
no, just down, no,
Oh,
in the
yeah,
middle where you have all the icons.
here. Oh,
That
you
is
mean this
indent
one?
and that's out there. Yes,
Okay, let me try this. Oh, wait. Oh,
that's helpful
alright.
because it does block indentation. Okay.
Okay. Um,
Okay.
so you mean like you don't um want to
Okay.
iterate for self because
So
I only have single self.
so what's happening? The reason it's crashing is you're assembling a list, but add data point only adds 1 point at a time. So instead of line 38, just move line 41 instead of line 38.
You mean like move the indent here?
You want it indented.
Um,
No, you need it indented because you're going to do it for every X value.
yeah.
Get rid of, you don't need line 38. 38 does not do anything. That does nothing.
Oh, okay, so I don't need to create a list as
No,
well.
no.
Oh, okay.
And I'm
Then I
not,
should
yeah, you don't need the four cell loop either.
because it's only
It's okay. I mean, it's the first time you do it, it always is tricky. So now, but you do need to indent line 39.
okay.
And now you need to replace concentration with value because you in line 36, you use the term word value. Okay, no,
Like
no
where
S, no S.
no X? Oh, okay. What?
Now try saving it.
Mm,
There you go.
but it doesn't. Oh, because I did it wrong.
Well, you probably don't
Oh,
have any chemical. Oh, there it is.
uh, uh, like,
That's because you're overwriting all the time. You're not erasing this. Now you want to do that erase function.
oh, yep. So,
So outside of the loop, you need to do the erase, but you want to do it before rather than afterwards. Otherwise, it'll blink on and off.
um,
And now this would be under scientific plots,
okay.
erase
Erase.
plot. Okay, that's it. Now try.
Um,
There you go.
oh, wait, that's,
Now you probably want to switch from displaying the cell field to displaying the chemical field in the graphics window on the left.
um,
There. Don't close it.
oh, okay. So,
Just change the pull down where it says cell field oxygen. There we go.
oh, okay.
And now hit run again.
Okay.
Okay, so
But
now
it's
it's
yeah, it's stable right now. It's a freezing still. I think it's stable because you can see like this curve doesn't change.
okay.
Neither.
All right. So, and which option did you take for the uh what are you doing with the cells? Are you secreting or absorbing or what are you doing? Here you
Oh,
have here you have basically chemical coming from the outside, you have decay and nothing else. Is that right?
yeah, I only like add the secretion plugin, and I didn't add code to the
Okay, that's
Python
fine.
yet.
But now you have the basic code. So now you want to create one frozen cell in the middle of the simulation
Mm.
and
Oh,
have it absorb or secrete. In this case, it's secrete.
okay, so now I could just add the secretion part.
Well, do you have a cell? Is there a cell in the simulation? Did you create a cell?
Yep, it's freeze. It's a free cell.
Well,
So it's like
I don't see it. That's why I'm.
here, like,
Oh,
but
you
it's
created
a
a
big
really
one.
big cell. Yeah, I'd make it smaller.
Oh, okay, okay.
I mean,
Oh,
it's okay to make it big, but I would make it a little bit. I would make it something like 10 by 10 or 7 by 7.
um,
There's
40.
nothing wrong with making it very large, but uh,
No,
I think
I'm
what
sorry.
happens will be clearer if it's small.
Um, let's do it
Okay.
now. Like the cell is smaller, and
Right. Okay. That looks fine. And you have that. Uh, is the cell doing anything now or no? It's just
no,
sitting there.
it's just yeah, it's just there.
Okay, fine. So let's also do one other thing though. Let's make the boundary conditions zero at the boundaries instead of the make the value zero and the at the edges at lines 50, 66, 65, 66.
But oh, I see. Um, so you mean like change them all to zero because
Yes, because
it's assigned by
you
position.
want the chemical to come from the cells, not from the bound. Now run it, you should have no chemical.
Okay. Yep.
Okay, good. So now let's make the cell secrete.
So
So now we have to go into the step function. And now
I
you're going to
to
need that 4 cell now.
okay. I'll just use
Try
this
it
one.
on your own I'll try it for a minute
Oh,
on your own and then I'll help. Okay.
okay. So 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 list. So, so yes, the short is good. Oh,
Again, I recommend using the CC3D Python Yapnagar. And this will be secretion and absorption.
yeah. Wait, you're like the question. Oh, trying all of them. Okay.
Right. Pick
Um,
one, any one. Pick one to begin with.
okay, I'll
Secrete
play.
inside cell or cadets. Anyone is. Okay,
Doesn't
good.
get one experience. 300.
That's fine. The one thing you'll probably want to do is, again, with only one cell, it doesn't matter, but you probably want to move that line 39, the field secretor. You don't want to put it inside of the loop. You only have to call it once.
Okay,
So you can move that up to line 34, basically.
up to one. Okay. Um,
There, that's perfect. Good. Okay, that should work. Now, question. You have a secretion rate of 300 here.
mm,
What's the decay rate?
I think I should, so to
Yeah, you defined a
zero
decay
point
rate.
0.
Right. So what's the equilibrium value going to be numerically?
I to calculate it. Um, but that's pretty large. So
Yeah,
it's
so you
like
probably want to make the secretion rate smaller
slow,
by a factor of
small.
1,000 or at least 100. I wouldn't know. Yeah, okay, good. Perfect. Let's try that. So that's good. I mean, the numerical value doesn't matter, but it's good to be aware of what that should be. Okay, so now what do you expect to see when you run this?
Um, I mean, like the highest value would appear at the boundary. So, um, oh, I didn't set the diffusion. No, I think I keep them identical. So, um, inside of the cell where at the medium, the diffusion thing will be the same,
Okay,
and you can see like the substance is just diffused to like outward to medium and
okay,
inward to the center of the cell with the same like rate.
great, perfect. So let's see.
Oh, that's pretty fast. So, um,
Look at the plot in your red plot.
okay. Uh,
You have exactly what you said. The concentration goes down on the outside. It goes down in the middle because you're only secreting at the edge, right?
yeah.
So that's what you expect. Now try inside cell instead of inside cell at boundary. So in line 40, you just you could just do it by hand. Just get rid of the words at boundary. Be easy.
Uh,
Okay.
it's
What do you think is going to happen now?
inside cell. Uh, so that was just like a like a spot source and diffuse. Um, like how do I say that? Like it's like a dot source, and all the substance is just diffuse. Um, to like every orientation. It's
Okay, so
like a
actually, okay,
circle.
let's see if that's right. Try it.
Okay. Uh, I,
It
I think
actually secretes everywhere inside the cell,
oh
all over the cell.
okay, but the cell is between 40 and 60, so why like it is not a plateau but like a peak here.
Because it's secreting everywhere, but you're only losing material at the edges, right? You have diffusion taking the chemical away near the boundaries of the cell. The chemical profiles for diffusion are not always exactly what you would expect. Uh, so there's effectively the cells at the very center of the cell, it's surrounded by other sources of the same chemical. And so that means there's less diffusion away from the source at the middle. And so that's why you get a higher value. Notice also the numerical value. When you had secretion just at the boundary, the maximum value was about 3. And now the numerical value is about 13 because you're secreting over all the pixels of the cell, not just over the boundary pixels. And so you have more cells secreting at the same, more voxels secreting at the same rate. So you're actually putting more chemical in this way than you were by secreting at the boundary.
Oh,
Now,
that's
try the next one, which is the one you were expecting, which is at COM.
oh okay. Uh,
And I think the syntax is AT capitals. Yeah, I think at, though. I think capital A, lowercase t, I think.
capital A. Where's the
Cell at COM.
so oh okay.
No, not add, at.
At
Yeah,
at oh, okay.
I think that's right. Otherwise, we'll have to look it up.
Okay.
Yeah, there you go. That's what you were expecting, right?
Okay, yeah, but oh, like there's a scalar here.
But it's also if you look, it's scaled by 1,000, I think, because you're only
Yeah,
secreting at 1 pixel now.
nice.
Okay. And there's one other one to do, which is you could secrete at a constant value.
Okay.
And you'll have to look up the syntax for that one. I don't know.
Uh, uh, secret. Oh, fuck. Oh, here. Sorry.
Constant concentration. There you go. So you don't need the secretor. You do need the other one. And again, make it 0.03 if that's what 0.3 if that's what you were using. Okay. And so now the concentration is the same everywhere inside of the cell. And so depending on where you secrete and how you secrete, you can get quite different results. And biologically, all of those different things may be appropriate in different situations. Sometimes the secretion rate really is a constant rate. At other times, the secretion really holds the concentration to a fixed value. Sometimes it's over the whole surface of the cell. Sometimes it's only in given locations. So all of these are possibly biologically meaningful depending on the situation. Okay. So that's how you use secretion. And let's see about uptake. So we did this already. You got these results already. Now let's try uptake.
Okay.
So let's now go back and have the chemical come from the boundary. So let's in the XML put your outside values to, sorry, you can't see. I'm trying to show you my screen
Oh,
and we'll see it.
okay, sorry.
Sorry, no, I forget. I'm so used to being a class set up where you don't. So now we don't have to change the diffusion and decay constants, but let's put the constant value plane position back to 10. So we have source from the outside. Okay.
Mm-hmm.
And then we're going to make the cell do, instead of making the cell secrete, we're going to do uptake inside cell 1 comma 0.1. So now instead of having the cell be a source of chemical, we're going to have the cell take chemical out of the environment. Okay. Try that. And actually, there is a reason. The reason it has this global decay constant to be 1/1,000 here instead of 1/100, which is what you had, is that if you have a decay constant of 1/100, the chemical doesn't get to the center. So you need to have a fairly small decay constant because you want really to see the uptake. So is it clear what you have to do? Change the global decay constant. You could even make the
Yeah,
global decay constant 0 if you wanted to. It would still work.
I'll
Uh,
just
but you need to use the uptake inside cell instead of secrete inside cell. Okay.
okay. Um,
Not all 4 of them, just one of them.
okay. I'll also like uptake inside cell at boundary.
That would be
Boundary.
fine. That would be fine.
Um,
Does that work?
Okay, I'm trying to yeah, I think it
Let's
works. Do you want to
let's
see
take a look.
the
Sure.
so here, like this is the like source
Okay.
from the outside.
Okay, great. So why don't we turn off, well, let's go back to your XML.
Oh, it doesn't, you think it doesn't reach the
Yeah, let's
net?
go back to the XML and
Mm,
actually make the decay constant in the to be 0. So in line 48, you have a decay constant of 0.01. With that, the chemical never gets to the cell. So you have to make that 0.
okay. Um,
In
but I
line
think
40,
like,
in line 48, you have a global decay constant of 0.01,
oh,
in which case
that's
the
all.
diffusion length was 10, which is going to not ever get there. Now try it. Now try it.
Okay, I got it.
There you go.
I would keep writing. It's like, it's screening like constantly. Wait, why it's not?
That's the correct profile. And what's a little puzzling is why you have any chemical getting into the center of the cell at all, uh, when you have uptake at the boundaries. And the answer is that you're not taking up 100% of the chemical.
Uh,
If you had uptake inside the cell instead of uptake inside cell at boundary, you wouldn't see any chemical inside the cell. So what you seem puzzled by this shape. Why is the shape puzzling?
actually, like, kind of like puzzled why the bottom of the curve doesn't rise because I think it'll keep rising because I guess the decay rate is set to be 0 and there is like a lot of substances continuously being put into the system. So I think the total amount of the substances should rise up.
Well, because you're reaching an equilibrium, right? You're taking the cell is absorbing the chemical
Hmm.
and it's absorbing the chemical as fast as it's being put into the environment. So now if you make the absorption rate different, you'll see that the equilibrium will be different. So if you go back to the Python, the secretor plugin, if you make the first one is the maximum uptake and the second one is the fractional uptake, make the fractional uptake smaller. Instead of 0.01, 0.1, make it 0.01.
Maybe the max one or
The
the
second one,
fractional
the
one?
second one, the fractional one, 0.01. What's going
Point.
to happen? What do you think is going to happen with that? Is the chemical concentration going to be bigger or smaller?
The fraction um but the fractional proxy only affect the speed and they take into
Right.
the
So there's going to be,
into
is there going to be more chemical or less chemical when you take up less?
less chemical.
No. Well, try it. See what happens. Remember, the minimum value is about 3 when you did it this way. Run it
Mm-hmm.
again. Now run it.
Oh,
The shape looks the same, right?
yep. But
But look at the
uh,
value of the minimum.
yeah,
It's 8 now instead of 3. You're taking
uh,
less chemical out of the environment So the total amount of chemical is more.
Oh, less. Sorry. Oh, that's a lot. Sorry, I probably like weird to digest. Maybe there is something like to
No, don't apologize. I want me, there's nobody waiting for us. We could take as much time as we need so that you understand.
oh, okay. Oh,
If it's
so
confusing, please ask. So I want to make sure that things are clear.
okay, so if I didn't understand it wrong, like the max, um, I mean like the second value in this parenthesis, refers to the maximum um value, like amount of that,
So
like once the amount of the boundary like reaches this value and it will just
no,
stop
so
at.
what happens is the following. For uptake, you cannot take up more chemical than there is. You can't take up more than there is because then the chemical concentration will go negative. So you are saying take up 1/100th, 0.01, 1/100th of the chemical that is available. So if there were 100, if there were, the concentration was 100, you would take up 1 unit. If the concentration was 5, you would take up 0.05 units.
Oh, okay.
However, if 0.05, if the concentration is, if that amount that you're taking up is bigger than 1, you take up 1. You don't
Oh,
take up
okay.
more than 1.
Oh,
So it
that's
takes up a linear, it takes up a constant fraction of what is available up to some maximum and then stops. So it
okay. I see.
saturates. So now change the 1 to a 10. It shouldn't make any difference. I don't think you're ever saturating it. So if I don't think run that, it won't change anything because you're still in the regime of being a linear uptake. Let's see if it's different.
Yeah, it's
Didn't
same like
change at
around.
all. Okay. Now go the other way. Make the maximum uptake 0.01 or 0.001. Okay. You're taking up less now. You're determined by the maximum, the maximum you can take out. It would be maybe clearer if you did not at uptake at boundary, but just did uptake inside cell. And then you'll see it'll look a little different. Then the minimum will be at the center of the cell. Try that. Try that.
Mhm.
I mean, this matters because if you have a tumor that's taking up, all the cells are taking up chemical, the concentration field can have very different profiles depending on whether the cells take up a lot or a little bit or only up to a certain amount. Notice how different the profile is now. The shape is quite different.
Yep, like so in the previous case, the minimum value appears at the boundary.
Right.
This
Now it's in the
uh,
center.
yeah, the center and and the end up value is
a little
smaller,
smaller. Yeah,
that means like the cell uptakes more.
right, because you have more voxels that are taking it up.
Mm.
So it's a little bit tricky. You have to do a little bit of hand calculation to decide what the value should be.
Oh,
The other thing let's play with, because I haven't done it yet, is let's use the reporter for how much you took up. So let's go
oh,
back to the Python for a second. And now let's paste in, let's see if we have it. This may be one of the one. Oh, there it is. It's up there. If you look in line 41,
yep. Oh, took them out.
you want to
Um,
count, you add the total count to that line. So uptake inside cell total count, just add the words total count.
I like
That works too.
okay. And but this one is for secretion, so I'll change.
Yeah, but it'll work. Just
Oh, oh, okay.
don't.
Sorry.
Well,
Um,
if you want to try editing it yourself, that's okay. But all I'm saying is all you need to do is copy the words total count and paste
mhm.
them at the end of the
Oh,
uptake
okay,
command.
okay. Int-
And now you have to make that equal to something. So look at the line just below. Look
Oh,
at
this
line
one.
55.
Yep.
Total amount equals,
Oh, okay. So, yeah, I think that works.
and then you need the dot total amount at the end.
Yep.
Okay. Now it's not printing that at the moment, so we have to display it somehow. But yeah, there we go. Total amount. And as I mentioned, it's going to return a negative number, so you're going to want to make print minus that value. Good. And now you can see how much the cat. Now you've got the number that you would care about. If you had a cancer cell that was taking up oxygen or glucose, this is telling you how much oxygen and glucose per time the cell has.
Which one?
Okay, so now we need to look at the
Um,
console, and you see it's taking up 4 units now. Whether 4 units is a big or a small number, I don't know. Um,
um, now it's like kind of like stable.
why don't we
I think.
why don't we stop and then hit step a few times, because it's interesting
Okay.
to see what it is at the very beginning.
Okay.
And then let's look in the console and look what those values are after a few steps. Step, 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 step. And it doesn't have any chemical yet. Now the chemical's beginning to reach the cell, taking up just a tiny bit. Keep
Okay.
stepping. Step for a while till the chemical gets to the cell. You see the amount taken up is going up gradually.
Mhm.
It's going to take a little while for it to get saturated. 0.5, 0.2, 3. And this is also telling you about the time, the diffusion time, how long the chemical takes to get from the edge to the center.
Okay.
If you used a diffusion constant of 1 and the distance is 50, then it's going to take something like 2,500 time steps to equilibrate. Actually, it's done a little bit faster than that. Maybe the diffusion constant was faster than I thought. Okay, so now it's around 3, and I think it saturates at 3.
Yeah, 3.999.
No, let's keep going. No, it's still going up. 4.
Yeah, like it doesn't change
Yeah,
anymore.
now it's okay, fine. So now you know the equilibrium.
Okay,
So that's not the most convenient thing in the world, but now you know how to control secretion and control absorption and how to measure how much you absorb.
okay, um,
Do you have any questions about that so far, or do you want to maybe try to apply this in a little bit of a more interested simulation?
so I think I still like have the question that as
Yeah,
we set the decay rate, like both decay rate as 0 here.
right.
So why does it like as it the uptake amount reaches around 4 and does not take in anything, it is set by the maximum or like this value or according to the equilibrium.
Well, this is equilibrated, so it's taking up 4 units per time step. So you have 4 units of chemical coming from the boundary that diffuses to the center and the cell takes it up.
Um,
If you made the maximum bigger, make the maximum 0.1 instead of 0.01 for the uptake. Okay, now try running it. Is the uptake amount going to go up or
optimum uptake would go up, I think.
Okay, so now let's look at the
Yeah, it's already
console.
going.
Let's look at the console and see how much
Okay.
chemical that the cell's taking up. 18.
18.
So it's taking up more. Not 10 times more, though. You made the maximum rate of uptake 10 times bigger, but the amount taken up went up by 6.
So that means like when it reaches equilibrium,
Yeah.
the cell takes more substance.
Yes, that's right. Now, what if you made the fractional uptake bigger? So now go back to your XML, sorry, your Python, and make instead of 0.01, make it 0.1. Now the actual concentration of the chemical will go down a lot compared to what you had before, but the uptake rate will go up. Try it. Because the chemical comes from the boundary, it has to go somewhere, and it goes into the cell. There's no other place for it to go. All right, so let's look at the uptake rate. 31.
Yeah.
So it's not so simple to calculate what the uptake rate will be as a function of those two values. And so what you do have, what's useful instead is to say, look at the chemical profile, look at the amount taken up, and then see if I increase the uptake rate, the amount taken up goes up by this much. And that's how you're going to tune the simulation. And so let's think about actually applying that now a little bit. So we did a whole variety of these. Didn't do every possible one, but we did a bunch of them. Something that can be quite interesting, which maybe we should skip for the moment, but you can try, is we had the chemical coming from the boundary, from a distance from the cell. But in sometimes, for example, in a tumor, if the stromal tissue is well vascularized, the stromal tissue may be the source. And in that case, you would simulate that by saying that there was a secretion by the medium. instead of by the boundaries. And if you do that, then basically the concentration in the medium is the same everywhere, like that. And then you just have uptake in the cell. So this is more like the single cell is behaving as if it were the whole tumor. And you can get different profiles, again, for different rules. And we did all these already. And so let's now try to build a simple tumor simulation. And the way we're going to do it is we're going to do it in a couple of steps. The first thing we'll do is we'll draw.
Hi, Professor. Sorry to interrupt. Do you want to like share your screen for now?
Oh, shoot. Am I still? I thought sorry. Haha. Did it not share?
It's okay. Yeah.
You are sharing, James. I think she is on the wrong
Wait.
tab. In Zoom, there are multiple tabs. You're probably in the meeting tab. There is a screen tab. Glazer screen.
Okay.
Do you see
Sorry,
that?
just a second. Oh, I see. Oh, sorry. It's my mistake.
Can you see the slides now?
Yeah, I can
All
see the
right.
slides.
I mean,
Thank you.
when you're going to use Zoom for things like this, in
Mhm.
class, of course, you have a laptop. We all have laptops. We're stuck. But if you're at home and you're going to do Zoom plus coding, it's really nice to have just even a very small, inexpensive second monitor,
Oh,
second screen, so that you can have the Zoom session or the slides on one screen, and then you can have your simulation on the other screen. I know when you're in class, but you only have, when you have your computer, you don't have that luxury. But I mean, where I have it now, I have the Zoom on one screen and the slide deck on the other screen. And if I were smart, I'd have a third screen where I could have the CompuCell running on that. So then I wouldn't have to switch back and forth. And there's no problem, but it makes life a little easier if you have an extra screen for this. What I've
sure.
thought about is getting one of those big for my desk, getting one of those big wraparound screens so that you could have everything on one huge screen. I don't have that. Okay, so let's talk about a very simple simulation of a tumor. You certainly, Paul does these in a more sophisticated way, but we're going to imagine that we have a tumor and it's going to have a proliferating zone at the boundary, and then it's going to have a quiescent zone and then a necrotic zone in the middle. Now, in reality, proliferation, necrosis, and quiescence are determined by both oxygen and glucose and growth factor availability. So the real situation, there are different signals for those different situations. But we're going to assume that we're going to just have the oxygen control everything to begin with. Okay. Again, the point of this is not so much to build a real cancer simulation. The point of it is to learn how to build a simulation. Then once you know how to do it for a simple case, if you want to do it for a more realistic case, it's easy to add. And so we're going to assume also, not right now, but at some point, that there's what's called a basal metabolism, so that the cells have some level of resources they need just to survive. If the cells have plenty of oxygen, they're going to grow and proliferate. If they have a medium level, they're going to be quiescent. If they don't have any resources, they're going to be necrotic. Now, in reality, some of these things are determined by ATP levels in the cell, which are buffered, not by the instantaneous amount of oxygen. So the model we're going to build is not a very realistic model of tumor. but it's to show us how we could build a model that's more sophisticated. Okay? And so what we're going to do is, and I hope it doesn't take too long to do it, we will build a little simulation where we have proliferating quiescent and necrotic cells in layers. And again, the diffusion of nutrients to the interior is limited by the uptake of the proliferative cells in the surface. And here's a comment. This is a Jim Sluka-like comment, which is that it's useful to do scaling of things like time per MCS, length per voxel, size of the cell lattice, and so on, in a block at the beginning of the simulation, so that if you would decide, gee, I want to make this is a problem for things that are specified in XML, because you can't do it for the XML specified things. There is a way to specify those in Python, but it's sort of ugly, and I'd rather not go over it right now. But you would like to be able to have scaling done in a consistent way. And this is really not my favorite way of doing things, but you can do this. You can declare you can declare, for example, suppose I say the uptake rate is 0.1. I could put that at the beginning of my Python. That's available as a parameter. I can't change the value in the classes, but it's available in all the classes. And then I could say, for example, the decay rate was, and here it's just I've made it a global variable in the shared steppable variables. It's another way of doing it. So those are just something to think about. For today, don't worry about too much, but if you're going to have things that you're going to be changing a lot, it's a good idea to put them in the header, or to put them in the global. So here we're defining, say, a quiescence threshold, a necrosis threshold, and I've written it as a ratio or a product because very often you'll want to rescale these by a constant amount. So for example, remember, if we want to keep the total concentration constant when we change the decay rate, we also have to change the secretion rate. So you might want to write the decay rate and the secretion rate are both equal to something times some value which we can change, so they change together. I don't want to make too much out of that now. That's something, Pedro, you maybe could help explain a little bit better going forward. But for the sorts of very simple things we're doing in class, it doesn't matter so much. But if you're going to write a complicated simulation, you would need to have all these things specified because they would represent real values from experiment. And in that case, it becomes quite important to put them in a consistent block in the code. And so it's good to get in the habit of defining these things in a consistent way. We don't have a schema. Unfortunately, we don't have a schema for doing this. We need one. So it's something to think about a little bit. So now let's actually do our tumor exercise. And in the first part of the tumor exercise, we're going to try to define what the uptake rates should be and what the thresholds should be for proliferating to quiescent, quiescent to proliferating, quiescent to necrotic. And if we try to do that at the same time as we have cell proliferation going on, it's complicated because everything interacts. And so the first thing we're going to do is we're going to create a circle of cells. Imagine our tumor has grown. And we're going to create a circle of cells. We're going to make them frozen. And we're going to have the oxygen field with constant value boundary conditions, because in a real tissue, the blood supply fixes the concentration of oxygen more than the flux of oxygen. And then we're going to have a diffusion coefficient. In reality, to make oxygen work the way oxygen does, we need diffusion constants of thousands, and everything would be so slow we couldn't do it. So we'll use a diffusion constant of 30, which is way lower than in reality, but it's manageable. Fast, but manageable. And we're going to create a tracking field for the oxygen in each cell. We're going to have the cells take up oxygen. And we'll use, to begin with, an uptake fraction of 0.1 and a maximum uptake of 1,000. And we'll use that total amount version of uptake so we can keep track of how much oxygen each cell is taking up. And then you'll use that plot that you did to plot the oxygen field across the center of the tumor. And you'll look at the total amount to see how much oxygen each cell takes up. And then you could try changing the max uptake, the uptake fraction, and see how things change. So you're just going to draw a circle of cells using blob initializer, freeze them. You had one cell that was frozen. This time you're going to draw a whole circle of cells. You'll switch the oxygen source to the boundary, but constant value boundary conditions. And you've already got the uptake and the reporter of the uptake written. So the only thing you have to do here is change the initial condition and add a tracking field for the chemical concentration. Okay? Give that a shot, and then if you need help, Pedro and I are here to help out. That might take a few minutes to do, so don't rush yourself. Just play with it.
Okay. Hi, Professor. I tried with the necrosis scenario, and
Okay,
I
let's
got a
see what you
plot,
get. Let's see what
but
you
I'm
get.
not sure if it's correct.
Okay, let's see what you get.
Um, so wait, okay, so this is the plot, and if you, if you think like that, it doesn't look quite correct.
Okay, so there's already something funny here, because I would expect this to be symmetrical, and it's not.
Yeah, maybe like I'm not sure if this.
So what are the boundary conditions we used? Let's look at the boundary conditions for the field first.
Okay, I think it's all 10 here.
Um,
I can like close all the.
so you want to use constant value boundary conditions.
Yeah, because like the um
You're using constant derivative boundary conditions.
derivative. Oh, probably I don't change this to Dirichlet's
Right.
conditions.
So you want to constant value.
So, so it's just constant value.
Yeah.
Okay.
But something else is strange too. Let's look at the blob initializer.
blood initializer.
Yeah.
Yep, here it is.
Okay. All right. So let's see what happens now. Let's try running.
Okay.
Okay, that
Is
looks
it
better.
uptake?
Now, what happened to your plot of the chemical concentration along the center of the
Oh,
center of
I
the
I annotated that lines, these lines with.
yeah, so you want to use that.
Oh, okay. Maybe I just copy the code from the previous code. These two lines and here.
Yeah, no, that's okay. Yeah, you got those set. That's good.
You,
Yeah, you don't need them
that
twice. So, yeah,
yep. And the last one's the window.
we'll do the plot.
Oh wait. Oh, wait. What are we? Okay.
That looks okay. And you probably want to make the range the x, the dim x, right? Self dot dim x, dim dot x.
No.
That's the kind of thing where you probably want to make it scale with the size of the simulation automatic.
And this one should be like this.
That's fine. But that's fine. Doing it by hand is okay. So now let's try that.
Okay. Okay.
What happened to the, there it
Oh,
is.
that was
There
hidden.
it is. Okay, good. That's fine. And now
It's
the other thing I asked you to do was put in a tracking field for the oxygen.
track and field.
Tracking field for the oxygen uptake. I want to know how much oxygen each cell is taking up.
Oh, 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 that one. Okay.
Right.
I
So
was like, I wasn't.
remember how to do that. You go to the init.
Just stop this. Track field. Alright. Oxygen. Track cell. Um, yeah. Professor, I think I got a problem here with the issue here.
Okay, do you remember how to? Okay, you can't give the field name. You should give the field name to the same name as the existing field.
So it's also like,
So you could give the field name oxygen uptake or something like that, but don't make it the same name as existing chemical field.
oh,
That oxygen there is okay. It doesn't, but that's fine too. Okay, that good. And so now you need to where do you measure the chemical concentration? Where you do the uptake, where do you do the uptake? Instead of printing minus total amount now, you now need to assign cell dot dict oxygen uptake equals whatever the
okay,
amount is.
I remember that. Um, oops, um, let's see. So, so, oxygen. Oops. Um, did I need to like add a object here? I kind of like forget here.
What's the problem?
Oh, I kind of like forget how we, if it's not okay to do that.
What did you just call it? You called it total amount in line 59.
Yeah, total amount.
So that's it. We total amount.
Oh,
Okay, try that. And now you'll have to add another window to display the uptake field. And that should give you all the information you need.
oxygen.
Okay. Now try running. So now you can read off how much oxygen is available to each cell. You can see what the oxygen profile is. And now if you change the fractional uptake or the maximum uptake, you could see how all of those things changed. But that's for this exercise, that's all that you need. The other thing you might want to do is turn on the contour lines if they're not on. Yes, they're on already, I think. Yes.
Zero.
All right. So why don't you just try changing one thing, like changing the fractional uptake rate or the diffusion constant, and see what happens to those. You have to first look at before you do that, you're going to have to look at the values, the numerical values. I think you're missing a minus sign probably for the oxygen concentrations, but
Around 1 and around minus 20. Maybe like
minus total amount.
signs here. Okay.
Okay, everything else looks fine.
So just like level up the fractional amount a little bit.
Right. Because you're going to set some thresholds, and those thresholds are going to depend on the availability of oxygen.
Mm-hmm.
So you can see what the maximum available is. You basically, the oxygen is only getting one layer or two layers into the tissue, right?
Mm-hmm.
Now, what's the uptake rule you're using, by the way?
It's like inside the cell.
Okay, that's fine. All right. But you're actually taking up a lot. I mean, the fractional uptake is quite high here.
Yup, like this value is like twice the previous case.
But if you go back to the uptake rule, you're
Uptake
taking
rule.
out where
One
in the Python where you're
a
doing
thousand.
uptake. The
Like
now it isn't doing anything. It's you're taking up you see you set the fractional uptake to 1. Does that make sense?
oh, so you like take all of the okay.
Right.
So let's
In
take like
reality, it might take up 3%, 5% of the available oxygen, maybe 10. So try
okay.
try 0.1. But you could
Zero
do
point
is you could keep changing it and see what you want is the oxygen to get about 3 cell diameters into the tissue. So you want to adjust that so it does. So try 0.1 and see what happens. So then you can try again.
point one.
Try 0.1,
Point
which is
one.
what you have.
Oh,
Run that.
okay. But like at the first the case is with the 0.1.
You'll have to wait for it to equilibrate for a minute.
Okay, let me just I think this is
Okay.
manually called out. This one is the same case like here would be like around 20.
I'm sorry I couldn't hear you.
Oh, like this value would ultimately be around 20,
Okay.
and this one like the minimum
And you'll notice
value.
that this time with the less uptake, you have more oxygen in the middle, right? The oxygen gets deeper into the tuber than it did before.
Mm-hmm. So, but for necrosis case, so
Yeah.
like the oxygen are expected not to reach that deep into the tumor, right?
Right. So, but you're going to be setting a threshold now, and you'll
Mhm.
have to look at what the threshold has to be. That's going to depend on the diffusion constants of the uptakes you set. So if we look at this, the cells in the middle get 9.
Mm.
The cells at the yellow ones get 14, and the red ones get something like 19. So write down those numbers somewhere. Okay. And so now, well, I suggested making a bigger tumor than the one you did, but it's okay. And a smaller screen so that it didn't take so long to run. But what you got here is fine. So now you can calculate what the diffusion length is. In this case, it would be the diffusion constant divided by the uptake rate, square root. And that's going to be given in voxels, and then you know what the size of the cells are. So you can determine it in terms of cell diameters. So in your case, you had a diffusion constant of what? 1? What did you use?
30? I
30.
remember that.
30. Okay.
It
And the uptake rate was 0.1?
uptake here it's 0.01.
0.01?
Point
What's the uptake
one.
rate by the cells?
Oh, the uptake behavior is settled in Python, so it should be like this one.
I can't see. I'm sharing the screen. If you have to tell me.
Oh, 0.1.
So 30 divided by 0.1 would be 300.
Mm-hmm.
The square root of 300 is about
170
okay, 17. Square
or
root
70.
about
170.
about 17. So, and the cells are about what size? 8 by 8?
8 by 8.
So 17 is how many cell diameters? It's 2 cell diameters. So you expect the oxygen to get 2 cell diameters into the tube for those
Yep.
parameters.
Yep.
Does that make sense?
17. Yep. Yeah,
So
that makes
again,
sense.
you know what the diffusion constant is. You know what the uptake rate is. The square root of diffusion over uptake is the diffusion length. That'll be in voxels. You know the cells are 8 voxels across, so then divide to get the number of cell diameters. All right. All right. So now this is something that you get. That's not too bad. We calculated 2 cell diameters, which is about right. And so now what we want to do, and actually, have I done that yet? No, okay. So now what we're going to do is we're going to add the quiescent and the necrotic cell types. And for the moment, they're not going to do anything different. They're just going to change. So now what you're going to do is you're going to measure the amount of oxygen available. And if the oxygen level is, you're going to have to create 2 new cell types in your simulation. Make them, you probably don't want them to be frozen. Maybe for various reasons, you don't want them to be frozen. So now you'll add 2 cell types. You'll add a quiescent cell and a necrotic cell. And then when you take up the oxygen, you're going to say if the concentration of oxygen is below a threshold, you're going to change the cell type from proliferating to quiescent. If the oxygen level is high enough, you change it back from quiescent to proliferating. If the oxygen level goes too low, you make quiescent to necrotic. Once you're necrotic, you can't come back. So it's a one-way transition. Do you think you could try doing that?
Try it, but probably it'll take some time.
So you need to add 2 cell types, and then in the loop where you calculate how much oxygen is available, you have if level above this and cell type equals this, then do this. So this is very much like what Paul would do with his rule grammar. And this is why I thought maybe writing a little coder that turns Paul's rule grammar into CompuCell would be easy, because this kind of thing we do all the time in CompuCell. You loop through all the cells, you check for a condition. If the condition is met, you change what the cell does. And so I'll give you a few minutes to try that on your own, and then you can screen share and we can try to work on it together if you're having trouble. Okay.
Professor, I have a question. Sorry. So is there any like um like thing written in Python, CC3 Python that we could get to know the number of the cell type currently? Or if there is no
Yeah.
Sure.
If you the
there is?
number of cell types, use this function. It's a Python function, len,
Then
and then inside the parentheses you put the list, of cells of a certain type, which is self dot
Okay.
cell list
Oh,
by
You
okay.
type.
want, do you want to, are you putting it in the chat?
Yes.
Okay.
Oh,
I was going to
okay,
say,
I
I
see
was
it.
going to
Thank
say I
you.
could
Thank you.
also let you have a whiteboard if you wanted it.
Okay, thank you.
Or screen share as well, because I don't know what you're trying to solve.
Oh, it's okay. I think I know that. I just added to the plot. Thank you. Hi, Professor. Now I have a structure, and in detail, it looks quite weird. So probably I can share my screen now.
Okay, great. Let's take a look.
Okay. So
Okay.
I think it's due to that I set two cell types as frozen, but
So what did you change?
so this is for adding a plot, and I like in each for iterating each cell, and I like add a decision of the cell type
Okay.
here.
Okay.
And so specifically on the cell type, if the cell type was one, that means it's a proliferating cell. And yeah,
Okay. So let's look at the XML where you created the cell types.
okay. So here I didn't. Yeah, like I said, the two types of them among them are frozen. So
So did you set a target volume for the cells?
no,
Did you set a
no,
contact energy for the cells?
no.
Okay, so if you don't freeze them, they're going to do strange things.
Okay,
So you
so
better make type 3 frozen too, otherwise it won't
okay,
behave right.
okay,
Now, the next step, you're going to unfreeze them, and then you're going to have to set those things. But for the moment, we were just looking at the change of cell type due to the chemical flip.
so okay.
Let's see what we get now.
But still like look quite weird. Like
Okay, so the source field, the chemical field, is not doing what you thought it should. Why did you change? Why did you change the boundary conditions?
oh, actually they it's still 10 and it's oh, wait, sorry, probably like uh, I didn't take them
Well, it's
here.
not. There's nothing to be sorry about. It just that it's not what you what it. It's not. It's different. It wasn't a bad thing, but it's okay.
Okay, so I think so. You see, like at this plot, initially, like we could see like there are three types of cells, but
Right.
like in a minute they just turn all red here.
So what is red?
Red means proliferating, so that
No,
means
I
like
don't
there
think so. What is red?
red here means proliferating cells.
You're
Uh,
sure?
yup. Like cell one. Red means cell one, and
No,
cell
but
one.
go to
Uh-huh.
player. Look at the
Oh,
player window.
oh, I got what you mean. Like red means this. Oh, sorry.
Right.
Uh,
Why is that? What's the additional concentration of oxygen
10.
in the middle?
Oh, you mean like you want to check the
What's the additional concentration of oxygen?
initial concentration of
At the
oxygen?
beginning, at time zero, what is the concentration of oxygen?
Okay, maybe we could step and have a look.
No, but
Um,
just look at the screen. What is the concentration of oxygen at time zero?
time zero. It's
How
just
much oxygen is there for the cells in the tumor at time zero?
It should be
Just
uh
look at the plot. Look at the plot
okay.
that you have at the bottom left of your screen. How much oxygen do they have?
0.
Zero. What happens when the cells see zero oxygen concentration? What is the
Um,
rule? What is the rule you specify?
necrosis. They all like died,
Right.
but
And once
um
they've become necrotic, can they come back?
no.
No. So there are two things you could do. You
Mm-hmm.
could either start out with a lot of oxygen everywhere, or you could say
Uh
that they don't read the oxygen concentration until the system has equilibrated. So you could only check the oxygen concentration after 500 Monte Carlo steps, for example. But the easiest
okay.
thing would be to start, you could start out with a oxygen concentration of 10 everywhere, for example.
Uh,
Then that might work. So why don't you try, which do you want to do? Do you want to delay things until it's equilibrated, or do you want to start with a high oxygen concentration? They're both legitimate strategies.
okay. No, I in principle I think I prefer the collaboration one,
Okay. So
but
in that case, yeah.
that would be like more complicated.
No, it takes only a few lines of code. So go back
Okay.
to your Python,
Oh,
and where is your set of rules about what the cells do?
I'm here.
Okay.
So
So
do you want
just
um
before line 66,
mhm.
before line 66, we say if MCS greater than 500,
Oh, um
colon. Yeah. And now you can use that indenter to move other things.
great. Oh, great.
Okay.
Oh,
Yeah.
okay.
So I wasn't
Uh,
so. Now
but
maybe you need to wait 1,000 steps instead of 500, but in any case, the principle is.
now like it's what is the multiple substrate?
So the other thing I don't understand is it looks like you have the uptake set to 1 again.
Update.
Yes.
uh,
The fractional uptake looks like it was set to 1.
Oh, wait. Let me see. Let me check. No, it's 0.1.
0.1? Hmm. Okay. That's interesting to me. I'm not sure why the oxygen is not penetrating the tumor then. Look at the plot. Look at the plot at the bottom left. The oxygen
Yeah.
concentration is essentially zero inside of the tumor.
Um, let me check the diffusion rate.
That looks fine. Everything there looks okay.
Mhm. Oh,
You
do you think?
probably, okay, so one thing that you want to know is you probably don't want to have a decay coefficient for the cells in addition to the diffusion. If you're doing uptake, you shouldn't have a decay coefficient
Okay.
because you're basically just doing the removal twice then, you know.
Do you think like it's because I only set not
Yeah,
only
you
set
can
the
make it, that's
diffusion.
fine. That shouldn't have, the 0.01 shouldn't do anything, but in line 56, for example, the
Mm.
diffusion coefficients are okay as long as they're the same. No. Oh, I see what it is. So why did you set a diffusion? Well, maybe it's correct. You set the diffusion coefficient of the cells to be very, very low. Why did you do that?
Maybe because like when the diffusion FE solver like the setting was saying that diffusion FE, I just noticed that like
That's okay,
the
but
frown too. So
I mean, in general, if you don't have to set, if you don't have a reason to set diffusion and decay inside of the cells separately, you don't need those lines. You could just take them out and have the global. Now you've got them set to be the same as the local, so it's okay, but you don't need to have it specified for the cells. Then it will default to the global value.
okay,
But that's fine.
another
Try
thing.
that. Try that now. This should look better. This should look better. The problem was that
Okay,
you basically had diffusion turned off inside of the cells. So now let's try it again. See what you get.
okay. It's pretty slow. Actually, like it doesn't transit the stat state yet because like the stats is still smaller than 500.
Okay, so that's looking better. So let's keep going. Let it run. See what happens. Okay, so all the cells are still what are your thresholds? Because the thing is, all the cells are whatever that green line is now.
Yeah,
What is the
green
green
line.
line? You should probably
And
add the plot. You can add the label,
legend.
the
Okay,
legend. Yeah,
in here. Uh,
I think it goes in line 22. The legend.
line 22.
Well, it would be line 25, I guess, at the end of it.
Oh, no, it's for grid, right?
Yeah, you need to
It's
add
not.
the legend. I know I never remember the syntax.
Oh,
So
okay.
I think that's right, but we'll see.
Mm, this is just double rerun it.
No.
Mm. Oh, it's not
Uh,
an
what is it?
argument.
Pedro, do you remember how to turn on the axis label, the series labels
Series labels.
in the scientific plot? If you wanted to say this is the green line is this, red line is this, and so on. Do you remember
Um,
what the
I never did that.
we did it
I
in class
can
a couple of weeks ago, so I could look there, but it's not one that's not one of the things that I have just at the top of my head. Uh, I
yeah.
have to look it up.
I have to check on. I can check on VS Code.
Well, whichever week we did plots, it's going to be there. So it's, but it is a little tricky to get the thresholds to work the way you want. So, I mean, this is the labeling is the least of it, but where's it? Plots. Okay, it's got a sort of an awkward syntax. I'll put it in the chat. Here.
Oh,
Oh yeah,
okay.
that's I was trying to understand that from what VS Code was telling me. Yes. Config options is
Okay,
a
let me try
dictionary,
it.
and then you put
Thank you.
the other entries there.
So
Yes.
let me try it again. Unmatched.
Yeah, I never did this,
Unmatched.
so this is new to me.
Um, just a second, let me share my screen again. So I just add the legend part into you can see the legend and we just wait till it runs to 500. Let me see it.
Okay. Okay, fine. So now we at least know which color is which.
Oh, blue one. Yeah, blue one refers to the
Yeah, well,
necrosis.
the color for the lines is not the same as the color for the cells. So
Uh, because like this color of the curve or the line here are
the
manually
color,
set by
right.
me. So yeah, it's different.
Yeah, it would be nice if you could set the colors when you declare the cell type, you should be able to declare the color. I don't know why we can't do that. That's something that should be easy to add.
Probably like we could do it
Yeah,
here.
but in any case, everybody becomes necrotic. Well, we could change it by hand here, and it will remember it. But you can't put it in the XML. You should be able to, when you declare the cell type, you should be able to declare the color. You can't,
Okay.
but you
Um,
can't. It does work. Okay, so this is
uh,
fine, but all the cells are dying because there's the oxygen level is too low.
yep. Um,
So that didn't work. So look at the values of the uptakes for the oxygen.
mhm. I
You're
found
showing the oxygen field twice, so you need to show the oxygen uptake field.
uptake. Okay.
And now you have to look at the numerical values, and they're 16,
Uh,
9, 4. And what were your thresholds?
it's 2.5, 3.5, and 7. So it's here. See like the total amount.
So
Yeah.
actually, that should be, it looks to me like that should work. I'm a bit surprised that that's making everything into necrotic stuff.
Yeah. Yeah, like all the cells like
The red
uptake.
ones should be proliferating, shouldn't they?
Mm-hmm.
And the green ones should be quiescent, and the blue ones should be necrotic.
But you can see here, like
But because the level doesn't matter. What matters is the amount available.
available.
Yes.
Okay. So like the total amount is like an amount that be accumulated for 500 monocolor stats instead of like the current concentration rate.
No, it's the current uptake that matters,
Mm-hmm.
which is what you have in the oxygen uptake plot. The red line is the concentration. The oxygen uptake plot is how much each cell is taking in of oxygen. That's the number you're triggering off of, I think.
Oh yeah, that's my rule.
Yeah.
So,
So Pedro, do you have an idea here? Let's look at the code and see what's going. If cell type equals 1, if total amount is less than 3.5, cell type is 2. If cell type is 2, total amount is greater than 7, cell type equals 1. Else, if total amount is less than 2.5, cell type equals 3. So why does everything become a 3? Let's do the opposite, the other option, which is let's
Is
start
it?
with a lot of oxygen. Or
I
did we,
think
are we
I
not
think the
reading the
reason
total amount right?
I think this total amount is a
Oh, you
negative
left out the
quantity.
minus sign. In line 65, you left out the minus sign.
Yep. Yep.
And now get rid of the minus sign in line 79.
Oh, in here. Oh,
You
no,
don't, you only need it once. You only need it once. So you can get rid of the minus sign in line 79.
oh, okay. I got it.
That's a
Yeah,
trap, isn't it?
yeah.
Yeah, it
Like
is.
Sometimes
something
the
that you.
simplest things are okay. So now the colors are different. Okay. I have to get to 500.
Mhm.
Shouldn't the cells switch type though?
She doesn't do it till 500 times
Ah,
500.
okay, okay.
We wanted to let the field equilibrate because at the beginning the field's 0. So if you switch immediately, then everything dies.
I
Ah,
feel like maybe next time we could set it to like 300.
Yeah, that'd probably be okay. Or you start with a constant value, or you start with oxygen everywhere and then let it decay. That's the
yeah,
other.
that's what we usually do. Yeah.
Anyway, it's only going to be another minute. Really. And you started with the constant cells all randomly different cell types. So, okay. Probably you want to start with all the cells proliferating.
Oh, this is randomized.
Yeah, but
It's
you really
randomized.
want all the
Still,
cells to be proliferating to begin with, or
still, they
quiesce.
should all die, huh?
No, I don't think so.
Doesn't change.
They don't die. You get no quiescent cells, and you get a lot of proliferating cells and some necrotic cells.
Oh,
But the field in the cells are basically zero.
Sorry?
Is that the field in the cells is basically zero?
No, but the uptake rate is not.
yeah. It
Ah,
depends on the total amount.
The uptake
So,
rate it's triggered off the uptake rate, not the value.
oh, okay.
oh, oh, maybe I should change it to this
Yeah,
one.
see there you
Now
can
it's
see clearly.
yep.
Okay, 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 okay. Yeah, that
So,
makes
but the
sense.
thing
Yes.
you do need to change is go back to your blob initializer
Block.
in the XML
Hmm.
and just create all of cell type 2 to begin with.
Oh, okay.
Or all of cell type 1. Make them all cell type 1. This
Yep.
cell type
So type one refers to the
is
proliferating.
proliferating. Yeah, there you go. And
Oh,
again, it's say, okay, now, and then make it 300 is fine. Now let's run it. So now we're close. We've got it pretty out.
mm,
And then not sure why it's slow. It was running much faster before. I'm not sure why it's slower. Anyway, it's working. Okay, 270. There we go. And what happened? They're all proliferating.
Um, Oxygen. Yeah, that depends on this plot. So all of the cells are like uptake more than at least like 3. So
Yeah,
they
so
would not.
yeah. So the thresholding is a little tricky. That's why I said actually in my slide, and we don't have to do that right now. That
Mhm.
was why in my slide, I suggested that, I'll come back to the slide for a second. That was why in my slide, I suggested you measure the mean available oxygen for proliferating cells. So actually, you look at the amount of oxygen that's available for all the proliferating cells, and then make the switch not based on an absolute threshold, but on a relative threshold based on what's there. Now, that's not very biological, but it makes it easier from the point of view of building the simulation, because then if you change the actual value, it doesn't change things so much. So, boy, we started at 3:30, right? So we've
Yep.
spent our time. Do you want to talk about what I'll do is I'll write up a little homework. If it's okay, I'll write up a little homework exercise to finish this project. Um, you should have gotten something that looks like what you got, except you should see layers of colors. And then the next thing to do is that quiescent cells actually don't take up as much oxygen as proliferating cells. And necrotic cells don't take up any oxygen, so you change the uptake rules. That makes it easier. And then the last thing is to actually have the cells grow at a rate that depends on the oxygen availability. First, you do it with no division, just growth, and then you add division to it, and you'll get something that looks like that.
Oh, okay.
This is if you have growth but no division, and then you can do it with division. And so you have all the pieces that you need. If you're going to have growth and division, you're going to have to add volume constraint, and you'll have to add contact energy. So you won't freeze the cells anymore. So maybe the first thing to do is add volume constraint and contact energy and unfreeze the cells with no growth. And it really
Okay.
shouldn't change anything. It should be just what you have now. And then you're going to say, okay, now I'm going to have growth. It depends on the available oxygen for the proliferating cells only. And then the last thing you'll do, then you can start with just 1 or 2 cells in the middle and have them grow. And you should see that you get a layered tumor from that. Now, if you also then have the necrotic cells disappear, then you have inward movement of the cells towards the center of the cluster, and you get these sort of these spiky shapes. You have that. So I'll write a simple assignment on that. We'll do the chemotaxis next week. So let's talk a little bit about a project. So tell me what you're thinking about. I mean, again, the thing you've already done with Paul is much more complex than the things we've done here. But if you wanted to do a simple model where, for example, you had a nutrient in the environment and you had 2 species of bacteria, just 2, and they consumed the nutrient and grew and divided, and 1 species of bacterium created a chemical that the other species needed, and 1 species created a chemical that inhibited or killed the other species. That you could do, something simple of that kind. You have all the pieces you need to do a simulation like that. So that's something you could do. Then you could gradually make that more realistic. Or, as I said, if you wanted to try to basically translate Paul's rules into our rules, you've seen how to make a little rule set. It's quite simple. You loop over the cells, you have if statements. That would be possible too. Pedro, what do you think about possibilities? But it's mainly you. I mean, it's your project. And we don't have too much time because we're a few weeks into
Actually,
the
like,
semester. But I want something that'll be interesting for you, but not too difficult, not too time consuming. So you tell me what you're thinking. You don't have to decide definitively today. But we should start talking about it. Maybe next week we can talk more. So tell me what you're thinking.
yeah, like Pedro and I actually talked about the like rule parsing part. So it's kind of like a supplement to Comstock 3D. Um, that is one aspect, and for the other aspect, I think maybe like simulating the antifreezing proteins, like how the ice crystals bind with these kind of proteins. But it's not like a single cellular organism. It's kind of like a more physical, like a big molecule combining. But I didn't
Sorry,
know like
somehow I didn't. I heard the word ice, but I didn't hear it. Some
oh
of the sound was not good. So say that again.
oh sorry. So like simulating the process of antifreezing proteins. Uh, have you heard of that before?
Well, I certainly know. I mean, I don't know about. I know about antifreeze proteins in fish.
Yep, definitely.
But
Proteins are
bacteria,
too.
I don't. But the problem is, I don't know how we could I don't. I mean, it's a fascinating thing, but I don't know how we would simulate that because we don't have any way of representing individual molecules. You could have a level of the protein that changed what the cell did under certain conditions. But what would you think? What would you think of as what would you simulate?
Like it could bind some ice crystals and to inhibit the ice crystal from growing. And
Right.
then
Okay.
uh, it's kind of like a very physics process because you need to like of course calculate the energy, maybe like for example like the chemical energy and things like that. But that's just an idea because I don't know like how Comsat 3D performs when simulating these big molecules interaction. So if you my tissue for it.
Yeah, I was saying, I mean, not sure how we would represent. I mean, generally we don't represent individual molecules in CompuCell or PhysiCell for that matter. Uh, we have field equations, which represent concentrations. Um, the only way you could do it in PhysiCell or CompuCell would be to make the molecules or the clusters of molecules represent. I mean, cells would have to represent clusters of molecules. And I don't know whether, I mean, you certainly could do something like that, where you have the cell represents ice, for example, and it takes free floating particles, which would represent water, out of the suspension, and you could coat the thing with a I mean, so in principle, you could represent that process, but I don't think this would be the best way to do that. Um, it's going to be slow and not very accurate. In other words, if you really want to do that, you're better off using a molecular dynamics simulation package, the kind of thing that Vikram does, I think. Um, I mean,
It's okay. It's just like
you could represent, so you could have a distribution of ice crystals inside the cell represented as a list of the number of crystals at each size, and then have a master equation, a non-spatial master equation for those. And then the growth rates would depend on the concentration of the antifreeze. But I, I think it's a very interesting question, but I don't know whether the techniques we're developing here would be the best way to solve it.
I got you mean. Uh, that's just an idea, and
Yeah.
I'm just like, um, see, like, if this works, but
So,
if it doesn't sound, it could be like, it could be like a plausible program or project. It's definitely okay.
so why don't you try, maybe Pedro, you could write a little bit of a cross nutrition model based on what we've just done here for a homework assignment. Could you write one up for me, Pedro? Where you
Cross
have
nutrition.
you have so here's what you do. So you have a background nutrient
Mm-hmm.
that comes from the boundary or from is produced by medium. And you have two cell types, A and B, and they both consume the background nutrient and grow at a slow rate. Okay?
Mm-hmm. Mm-hmm.
And the cells then metabolize that nutrient and produce a waste product, which they secrete. And they secrete different waste products. So you have now three chemical fields. You have background nutrient, you have waste product one and waste product two.
Mm-hmm.
And now cells of type A take up the waste product of cell type B and grow faster when they have it. And cells of type B take up the waste product of cell type A and grow faster when they have it. Okay?
Mm-hmm.
And now you do the same thing, except now cells of type B actually are inhibited rather than promoted by the waste product of A. How's that?
Sounds good.
That's
Sounds
the
like interesting.
that's basically, I mean, what she's got already now with her multi-species bacterial biofilms is
Mm-hmm.
basically that with 30 species instead of two.
Mm-hmm.
But that would illustrate the principles again of how to build that more complex model, because the complex model would basically be repeating that 30 times, but the structure computationally would be the same. And that maybe isn't a project, that's a homework problem, but at least we could do that as a homework problem. And then if, depending on how that works, we could think about whether you could make this more like your big multi-species simulation that you're doing with Paul. Would that be okay for this week?
Uh, yeah, I think so. Um, I think like the aspects that you mentioned, including like growth and division, degree uptake, that already like composed of this scenario, the nutrition, cross-fitting nutrition.
Right.
Um, so but for the parsing problem that you mentioned, I think the things that I've been worrying is I think I didn't have experience for writing code for a
No,
parser before.
that's okay. You don't, if you don't want to do it, don't do it.
No, no, no.
That's the kind of thing where I would say, if you were going to do it, I would use Claude Pro or Gemini Pro to help write the code, because those
Yeah,
kind of parsers and code generators are not difficult, but they're fussy, and so but you have to know enough CompuCell and enough PhysiCell to know what you're doing,
yeah. I
because
think
those
like
code
the
generators
real,
will give you 90% of what you need, but not 100%.
yeah, like the real. I think the real difficulty lies at the structure of like how CompuCell 30 was organized.
Right.
And I mean like it's not that I don't want to do it. Actually, like I'm pretty interested in it because I think that would help me to gain insights of a package or software
Yeah,
more, but I'm just worried that whether I can accomplish this in one semester.
right. I hear you. Pedro, what do you think?
I think it's reasonable. Uh,
To
I
try to
don't.
do the code generation?
Oh yeah, the code generation is very ChatGPT-able, in my
Yeah.
opinion.
I mean, doesn't when you use Physicell Studio to generate the scripts for Paul's rule grammar, does it output it as a comma separated list? Does it output it as XML? What does it do?
But it output a CSV file,
Okay,
and actually you
so
could load the CSV file into the graphics like,
right,
GUI
so right,
as well. Yes.
so in that case, presumably we could take that CSV file, parse it, and
Mm-hmm,
make again, you have a loop over all cells by type,
mm-hmm,
and you apply the rules. And the thing that would be tricky is that in CompuCell you don't have a registry of all of the variables that's available to you. So the user will have to get the names of the variables right. But I really think that uh, if you play a little bit, so try this getting this little tumor simulation where you have the cell types changing under rules
mm-hmm.
in CompuCell. And if you get familiar with how that looping to apply rules works in CompuCell, well, basically do the homework exercise for this week where you'll apply those rules in CompuCell. And then you can say, okay, here's some very simple rules. If the oxygen concentration is above this, do this. If the oxygen concentration is below this, do this. Basically, what you'd make is a table of rules just like that, except you'd read them out of the CSV file. And I think that Pedro is right that doing that, oh, you have to know the basics of how these things are structured. But I think ChatGPT or Claude Code Assist or Microsoft Code Assist, um, once you know what you want to do, it would generate the parser pretty well for you. I don't think it will be too bad to do it because literally there each line of Paul's rule grammar gives you one line of Python. I mean, literally it's a one line to one line thing. I don't think that maybe you have to do a little bit of loading things in and out of dictionaries, but I don't think it's much more than that. Unless there's something really different that I don't understand, Pedro, about this. And Randy said he would be willing to help.
And that will help as well.
Oh, thank you. Okay,
But
so I,
but
I
again,
think I can try that.
I don't want to force you to do it. In other words, I don't want to force you to do something you don't want to do.
No, I'm happy to do it. And no
But
worries
I
that
think if we did do it, we probably could publish.
um okay, I think
It
I'd love to
certainly
take
could be put into the CompuCell data, the CompuCell code base. So at least you'd have your name as a CompuCell developer if it worked. So it's I don't think it's a waste of your time to do it.
okay,
Um,
I'd love to
but
take
again,
challenges.
if you
Thank you.
don't want to do it,
Mhm.
um, don't feel that I'm pressuring you. I'm happy to work on something about something else, whether it's bacterial cross feeding or something else. Um, and we can do both in a sense. We can do a little exercises on cross feeding, simple ones, and then maybe make them a little more complex as we go forward and see how it goes. But why don't you talk to Randy and ask the question if you wanted to use Physicell Studio. I mean, if Physicell Studio exports it as a CSV, then we don't have to change Physicell Studio. I mean, it would be nice to be able to run just those windows of Physicell Studio separately. But if not, what we want to do is look at the CSVs and ask the question, what's the structure of the CSV? And then I literally think if you say to ChatGPT or Claude, I want to turn this into a Python loop that iterates over all individuals and then evaluates these individual lines as the following syntax. I think it will give it to you. I think it will it work 100% from the beginning? I don't think so, but I really think I don't think it's going to be too bad. So maybe Pedro, could you find a time later in the week to meet together and look at that together?
Yeah, this week, Thursday would be a good time. Thursday afternoon, around class time.
If you're free. I don't let me look at my calendar, but I think Thursday afternoon. Thursday afternoon, I'm stuck. So, but if you two can meet together for an hour to look at this, because basically you need to look at what the CSV structure is. And you may not be able to parse every possible rule, but the basic rules, it's basically hill functions. And you either have an ODE response to the hill function, deterministic response to the hill function, you roll the dice and you have a probability transition. I don't think there's much more than that.
Yeah, actually, I think the part like for that part it's kind of easy. And
Yeah,
I asked GPT about the structure, so you could already like give me like a streamline of doing that, including like parsing and
yeah,
constructing the abstract syntax tree and then generating code based on
yeah,
that kind of like a
yeah.
tree. So so yeah, probably I could like start doing that. Do you want me to like, join your talking this Thursday afternoon? Or
So you make an appointment with Pedro, and you and
uh
Pedro talk about it. I won't be this Thursday. I'm
okay.
tied up all day.
Okay,
So
so
you meet up with Pedro about it, and then next week, either in class or separately, we'll talk about it. Pedro is a
okay.
better coder than I am, so he can probably help you better than I can.
Okay, so probably before like Pedro meets, I think I need to do more investigations. So probably
Well,
like Thursday.
if you don't want to meet with him, that's okay. But I wouldn't be shy. In other words,
Okay,
the only reason not to meet with Pedro this week is if you're afraid that he's going to do it all for you, because it's not fun for you if he does everything. But if you
yeah,
feel, but you don't have to feel, but you don't have to be prepared. In other words, if what you do is open up Paul's paper or look at the CSV together or look at CompuCell together for an hour, that's okay. You don't have to be prepared. You can do the reading and the preparation on the fly with Pedro, because he can ask you questions. What about this? What about this? And then you can look it up. I'd rather have you meet for even half an hour and
Hmm.
just talk.
Pedro, are you like you're familiar with Visual Studio, right?
With Physicell Studio, I've used it in the past. I did a project on it, but
Yeah, so
I don't use it like daily, so limited.
uh okay, I think it's still pretty
So
familiar.
you can teach
Okay,
Pedro.
we can.
You can teach Pedro.
Okay, I think like probably we can meet.
Record it. So if you're teaching it, I can watch it afterwards and learn to.
Oh, okay, okay, okay.
Can you
So do
send
you
me
want
your
to
email?
schedule? Okay, okay, of course.
'Cause I'm creating the event here, but I don't have your email.
I mean, I don't want to make you uncomfortable. I want to be supportive. But the reason I'm always nervous when a student says they want to read or think about it more before they meet. I don't think you're like that, but I've had many students who said that and then never met. And
We never feel
because if
prepared
you
for
want to be
anything.
fully prepared, you never meet because you're
Yeah.
never fully prepared. And so it's better to just meet, and then if nothing, even if nothing happens, you've met, and then you meet another time. Don't be
Okay.
shy. You don't have to be. Things do not have to be perfect. Really.
Can you put your email in the chat,
Okay.
please?
Okay. Um,
And then Pedro, we need to pull out the little tumor. Basically, this exercise is a homework assignment. We have it, I think,
Mm-hmm.
but we have to find it and do it, and then create that cross-feeding bacterial simulation. That's actually a problem that we had in just the diffusion solvers, where you have two cells, one cell secretes the thing and the other cell absorbs it, and vice versa, and you get the sort of dipole fields when you do that.
Mm-hmm.
I thought about doing that exercise, and that we didn't have time in class. But that's a sort of a nice one. You
let
get
me see.
shadowing and that kind of thing.
Yeah.
So Friday morning. Friday morning. New Zealand time. Okay, I received the invitation link, and okay, I think I could at least prepare as much as I could before.
But don't worry, please. Just
Okay,
we're very relaxed.
Yeah,
okay,
I
thank
have
you.
an
We
idea.
want to support you. That's the main thing.
Yeah, we'll
Mm,
mainly figure out what are what are the things we understand, what we have to figure out, and
And as I say,
yeah,
Randy is very enthusiastic. He wants this to happen.
yeah.
yeah. Randy and I would meet every Friday. Because this semester I'm still doing rotation pulse lab,
Right,
so yeah, we could meet and I could just ask him if I had
right,
questions.
great. But
Thank
that's
you.
another reason to get started as soon as possible, because I know he's busy, so we want to make sure that he has time to help. Great. Okay, anything else you want to go over today?
Um, no. The last
I'm
thing is,
sorry about the ice, but I can
it's
imagine how to do it, but I think it would not be the best. I think that's much more likely to be frustrating than the other projects.
it's okay. Every scenario has its fit tool.
Different methodologies are
Mhm.
better for different purposes. It's not that you couldn't do it, but it's going to be awkward, and
Oh,
it's better to use the right tool. And I don't think this is the right.
okay.
Okay. Anything else?
Mhm.
We've had a long. Goodness, it's been full. We started at 3:30, so it's 3.5 hours. So it's a long afternoon. We didn't even take a break. So I apologize for not giving you a break.
No,
Uh,
thank you all.
all right. Okay. And thank you for being flexible about doing it online. But I didn't, as I say, I would have had to come back to the house and then come back to the university. And it then we would have had to start quite a bit later. So this was made it easier. All right.
Right.
Hey, you and Pedro, you and two have a appointment then set up?
Right now,
Yes.
I'm not going to the dance class because I'm sick,
Oh, I'm
so
sorry.
I'll stick around if you need.
No, no, but no, but did you need to talk to me?
Uh, I mean, I have stuff to talk about, but not
No,
urgent.
no, I was just making sure that you and Xiaoyu had made
Uh,
an appointment to meet later in the week.
Yep.
oh yeah, we did, yeah.
Okay, fine. So, and Xiaoyu, do you have anything else you want to talk about now?
Not for now. Thank
Okay,
you.
okay, thank you. So then class is over officially. Pedro, if you want to stay on and talk for a minute, we can, but I'm tired too.
See
Okay,
you
thank you so
guys
much.
later.
Okay,
All
bye.
right. See
Thank
you.
you. Thank you. Bye.
So the only thing I would ask is to get the parameter uncertainty. I have to do chi-squared statistics on the
Hold on a
parameters.
second, where's that? Am I still?
Screen sharing, yes.
The screen share I'm not worried about.